Crunch, 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 crunch. Crunch, 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 crunch. Crunch, 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 crunch. Ooh, pretty colors. Whoa. Sound. Dink-a-dink. The objective of this lab is to measure the speed of sound. You're going to do this by sending a sound wave via frequency generator into a resonance tube that will trap that wave and create a standing wave. You are then going to have a pickup microphone that you will move along the resonance tube to help show how the standing wave changes as the position of the mic changes. Now, you're going to be able to see how it changes through the oscilloscope. The microphone will take the sound wave information, transfer it to the oscilloscope, and you will see the actual image on the oscilloscope change. So let's talk about sound for a minute. Sound moves in longitudinal waves. That means that the molecules of gas, liquid, or solid, whatever the sound is moving through, oscillate back and forth along the line of propagation. Basically, the line of the molecules will alternate between compressing and rarefying or expanding within the medium. Whatever gas, liquid, solid, that's your medium. Now, for practical reasons, basically I'm too lazy to actually draw longitudinal waves constantly. I'm going to draw transverse waves throughout the rest of the video. Transverse waves have a travel direction that is perpendicular to the disturbance of the medium. So if I have my wave pulse moving in this direction, I'll see a disturbance in whatever medium I have moving perpendicular to that. So in this case, it would be up and down. So it just makes it a little bit easier to visualize some of the terminology that we have to talk about. Now let's get to that terminology. So we have a transverse wave that is creating a disturbance perpendicular to its direction of propagation. This type of motion is something that we are more familiar with as simple harmonic motion. Looking at this wave, from the midline of the wave to any point on the wave is called its amplitude. Now the distance from crest to crest is the wavelength. The time it takes for one cycle of the wave is called the period, and that's in units of seconds. How frequently one of those cycles occurs is called the frequency, and that has units of 1/seconds. Now, we find the speed of the wave to be the wavelength over the period, or the frequency times the wavelength. Now, because the speed of the wave is defined by the frequency and wavelength, this relationship applies to all harmonic waves. The propagation of the wave through a medium depends upon the elastic properties of the medium. For a compression wave or a sound wave traveling in a liquid or gas, the speed is given by V is equal to the square root of B over rho, where B is the bulk modulus of the elasticity of the medium and rho is the density. For sound waves, we say that the bulk modulus elasticity is equal to gamma times P, where gamma is a constant that depends on the type of gas and turns out to be a ratio of the specific heat at constant pressure of the gas and the specific heat at constant volume, and P is the pressure of the gas. Now, by Boyle's law, the ratio of pressure over density, P over rho, is constant for a gas at constant temperature. So the speed of sound is independent of pressure as long as the temperature is kept constant. The effect of temperature on the speed of sound may be derived by considering how the density changes with temperature. If V naught is the volume of the gas, of a given mass of gas at 0 degrees Celsius, and V of T is the volume at some temperature, the relationship between V of T and V naught is V of T equals to V naught times 1 plus beta T, where beta is the volume coefficient of expansion at constant pressure and has a value of 1/273 per degree Celsius of an ideal gas, and T is the temperature at which you're looking. Since the density of the gas is defined by mass, at mass per unit volume, the previous equation leads to rho equals rho naught over 1 plus beta T. Substituting that back into our equation for velocity, we get velocity at a specific temperature equal to V naught times the square root of 1 plus beta T. Now, where V naught is the speed of sound at 0 degrees Celsius, V of T is the speed at some temperature. This expression may be approximated by expanding the square root as a binomial expansion. So 1 plus beta T is 1/2 equals 1 plus 1/2 beta T minus 1/8 beta T squared plus So since beta T is near room temperature, we can get sufficient accuracy for most purposes by using only the first two terms of the expansion. This gives speed at a specific temperature is equal to speed at 0 degrees Celsius times 1 plus 0.00183 times temperature T as your speed of sound at a given temperature. So what we're going to do now is look at how we are actually going to measure the speed of sound with our resonance tube. So you're going to send a frequency into the resonance tube, and it's going to go through the tube, and then once it hits the end of the tube, it's going to bounce back. And so what that's going to do is it's going to create a standing wave. So you're going to get this standing wave where you have sections of constructive interference and destructive interference. Constructive interference when the two waves complement each other and you're still able to hear things, and destructive is when they cancel each other out. And so when they cancel each other out, you'll get these things called nodes. And when they're amplifying each other, you'll get these things called antinodes. And so what you're going to do is identify your nodes and antinodes. And by identifying your nodes and antinodes, you'll be able to measure a full wavelength. And so you're going to do that by marking each node and antinode, so measuring depending on, so how you're going to do that is by sending your mic into your resonance tube, and like I said before, your mic will then be connected to the oscilloscope where you'll be able to see the changes of the standing wave as you move your mic along the length of the tube. So you're going to go ahead and start at the very beginning, closest to the speaker, and you're going to identify your first node. So what you're going to see on your oscilloscope is just a straight line. And from there, you're going to identify your first antinode, where you'll see a full sine wave. And you're just going to continue all the way down your resonance tube. And so what you're going to do is you're going to look at the information that you've gotten and say that you have a setup similar to this where R1 is your first node, R2 is your first antinode, R3 node, R4 da 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 da. And so you're going to go for your first wavelength, and that will be from R1 to R5. Okay? And so to find a single wavelength, you're going to subtract R1 from R5. And then you're going to continue on R2 from R6, da 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 da. And then you'll take an average after you've gone the full length of your tube, finding your wavelengths. You take an average of your wavelengths, and then you'll have your average wavelength at the specific frequency that you're using. And then you will be able to calculate your speed of sound using V equals lambda times the frequency, where frequency is given to you by your signal generator and lambda is the wavelengths that you just measured. You're going to repeat that at another frequency and then calculate your percent difference. So now you're going to get into the analysis aspect of your lab, where you're going to be calculating V0, the speed of sound at 0 degrees Celsius. So you've found the speed of sound at room temperature using your measurements and calculations from before. Now you're going to use V of t is equal to V0 times 1 plus 0.00183 times t to calculate your V0. So you're going to do that, and that will be your experimental speed of sound at 0 degrees Celsius. Then you will use V equals square root of gamma times RT over M to calculate your theoretical speed of sound at 0 degrees, where R is your gas constant, equal to 8.314 joules over moles times Kelvin. Gamma is 1.4, T is 273 Kelvin, equal to 0 degrees Celsius, and M is the molecular mass of air, which we can help you with. Then you'll calculate percent error, and you're done. And that's the lab. Yay!